Start. Um, right. So, hello everyone. I'm Srishi Siddharth. I'm a PhD student associated with the Center for Systems and Control at IIT Bombay. And I'm also a TA for this course, W46 Linear Dynamical Systems. So, welcome to fourth week's tutorial session. So, let's begin with recalling the topics discussed during the week. So, let's see. So, the following topics were discussed. The first one being the controllability test. So there was a matrix test, vector test, then we looked at a notion called standard form for uncontrollable systems. Which we talk about decomposition. So decomposition and the transformation matrix T. After controllability, we talk about PVH test for stabilisability. Of discrete system as well as discretized systems. So we'll talk about all these topics today. So let's begin. So the first one is on controllability test. Let me write down the question. So consider the following LTI system. X dot equals AX plus BU. The matrix is R. A is 0, 1, minus 1, 0. And B is 1, 1. Okay. So verify whether the above system is controllable using the following tests. So we have the first one, which is the test using the controllability matrix. We also saw how to perform this test in the last week's session. And then finally the PBH test. Okay, so let's begin. So we'll start with the first part. We have a simple second order system. So the controllability matrix is simply V and A. So AP is 0, 1 minus 1, 0 times 1, 1. And this is equal to 1 and minus 1. So the controllability matrix is, since this is a square matrix, to check its rank, we can simply compute its determinant, which implies that the system or the pair AB, so let me write this down, the pair AB is controllable. Okay. Now we'll perform the PBH test. So PBH test requires eigenvalues. So we'll first compute the eigenvalues of A. That is computed by determinant of A minus lambda equals 0, which is no. So we have minus lambda and minus lambda here. Then we have 1 and minus 1. This is simply lambda squared plus 1 equals 0, which implies that lambda is alright. So let's recall the PBH test first. So the tests for PBS for controllability and stabilisabilities are different. So I write down the one for controllability. So it's the rank of E minus lambda I, B should be N for all eigenvalues in the complex pair. Okay. So the difference between the PBS test for controllability and stabilisability will be here, and we'll discuss it when we get to the stabilisability part. Alright. So we have for lambda equals plus I, A minus lambda I becomes minus I, 1 and minus 1. So we have to compute the rank of the matrix minus I and minus 1, 1 minus I, and B is 1, 1. So now this is not a square matrix. We have to determine whether the two rows are linearly independent or not. So let's see. Alpha 1 times minus I 1, 1 plus alpha 2 times minus 1 minus I. So we have to check if this implies that alpha 1 and alpha 2 are 0. So let's see. The first equation is minus alpha I minus alpha 2 equals 0. Then we have alpha 1 minus alpha 2 I equals 0 and alpha 1 plus alpha 2 equals 0. This implies that alpha 1 is negative of alpha 2. And let's substitute this here. We get alpha 2I minus alpha 2 equals 0. Just check this. So this implies alpha 2 times I minus 1 is 0, which is implies that alpha 2 is 0. And since alpha 1 is negative of alpha 2, this implies that alpha 1 is also 0. So we can quickly perform the tests for lambda equals minus I as well. But before this, we get that the rank is 2 because both the rows are linearly independent. Similarly, for lambda equals minus I, we have ramp of, let's see, uh, plus I plus I. This is A minus lambda I, and this is beta. All right, so let's just quickly check. Alpha 1, I1 1 plus alpha 2 minus 1, I1 is 0. So this is the 0 vector. Similarly, here, zero. So the last equation is again alpha 1 plus alpha 2 equals 0. You see that second equation is alpha 1 plus alpha 2 I equals 0. And when you substitute, we get I minus 1 equals 0, which implies that both the coefficients are 0. Therefore, the rank is equal to 1. Sorry, it's equal to 2. Therefore, the pair will be controllable. So I hope this question was clear. Now let's come down to the next question. Alright. So the next question deals with the decomposition for uncontrollable systems. Let's see. Question 2. So consider the LTI system. Stop equals minus 305 040 50 minus times x plus the b vector 111. So the first part of the question is the similarity transformation which transforms the system to the standard form for uncontrollable systems. And the next part is to determine its controllable subspace. So let's find out the transformation which transforms the system to the standard form. First of all, let's see if the pair AB is controllable or not. So we have a n equals 3. Simply A, AB, and A squared. Alright, so let's compute AB first. As 305 0, 4, 0, 5, 0 minus 3, 1, 1, 1. Odd. So the first one is 2, then we have 4, then we have a square b, which is simply a times ab, which is minus 3, 0, 5, 0, 4, 0. So this becomes, this is 4, this is 16, this is 4. Alright, so let's form the controllability matrix. The B vector is 1, 1, 1. Then we have 2, 4, 2, 4, 16, 4. Alright, so this is a 3 by 3 matrix. So let's just compute the determinant. This is 16 minus 32 minus 2 times 4 minus 16 plus 4 times 2 minus 4. So we have minus 16. Then let's see, then we have minus 2 times minus 12 plus 4 times minus 2. Alright, so this means that the rank, the controllability matrix is not 3, which implies that the pair AB is not controllable. That's why we have to find out the standard form for uncontrollable system. We have to decompose it into a controllable part and an uncontrollable part. Is not controllable. Alright. So let's see which. So this is not 3, so the rank can be either 1 or 2, right? So let's see if any two rows or columns are linearly independent or not. So we have let's see, 1, 1, 1. So let's check if these two are linearly independent. We have the equations alpha 1 plus 2 alpha 2 equals 0. And then alpha 1 plus 4 alpha 2 equals 0. The third equation and the first are is 0. Okay, so we can just subtract these two, and this would imply that 2 alpha 2 equals 0, which implies that alpha 2 is 0 and alpha 1 is also 0. So columns 1 and 2 are linearly independent. Similarly, we can check for columns 1 and 3. So what remains is checking columns 2 and 3. Let's see. We have alpha 1, 2, 4, 2, 4, 16, 4. So we have 2 alpha 1 plus 4 alpha 2 equals 0. And 4 alpha 1 plus 16 alpha 2 equals 0. Let's see. Okay. Just 1 second. Yeah, so this also implies that alpha 1 and alpha 2 are 0. So what's not true is that the linear combination of the three columns one, 1, 1 2, 4, 2, 4, 16, 4 does not imply that alpha 1, alpha 2, and alpha 3 are 0 because we have just found out that the rank is not 3. So what we can conclude that there are two linearly independent vectors or columns of the controllability matrix. So these columns would help us to construct the transformation matrix. Let's select any two of the linearly independent columns. So let's select 1, 1, 1, and say 2, 4, 2. Like, why? Because the dimension of the controllable subspace is the rank of the controllability matrix. And we denoted by, you can see from the lecture, it's n bar is 2. So it's a two-dimensional subspace. So it would have two linearly independent vectors. So to simplify this, so that we don't have a complicated vector 2, 4, 2, what we can do is keep this one as it is and select some other linearly independent vector for R2 because this implies that the controllable subspace is R2. So let's see, we can have 0, 1, 0. We can still check that these are linearly independent. Since we want the transformation matrix P and it should be invertible, which implies that T should be an n by n matrix, where n equals 3. So what we need to define is, not define, now we have to select a third vector, which is linearly independent from these two. So we can just select a basis vector for R3 that is 0, 0, 1. Or maybe let's say 1, 0, 0. You can again check that these are linearly independent. So what we have to do now is that we have this T, which can be constructed by placing the columns 0, 1, 0 and 1, 0, 0. We can check the determinant, which is simply 1 and 0, 1, 1, 0. And the transformation matrix is invertible. Alright, so we have T inverse then. So let's say that after the transformation, we have new states x tilde, which are given by T inverse of x. Okay. So then we have x tilde dot equals T inverse x dot. And now we just substitute this ax plus b. And since this is a system in x tilde dot, so we need to substitute x also. So it's T inverse at times x tilde plus T inverse b. So now we have new matrices. Let's denote them as A tilde and B tilde. Similarly, for the output equation, we would have y equals cx plus du, which is c T inverse x tilde plus d. This is the new C matrix. Alright, so let's just compute what T inverse B looks like. To write down first what T inverse is, you can calculate this. Or you can check in MATLAB too. It's a 3 by 3 matrix. So 0, 0, 0, 0, 1, minus 1, 1, 0, minus 1. So T inverse B is going to be order of the elements. So we have zeros, 0, 0. So the inverse is not correct. So just check what this is because I think it's like 1, 0, and 0. So there's I guess some kind of mistake here. So T is alright. So I'll just write down what T inverse AP is. Compute this as well. I'm going to write this down directly. 2, 0, minus 5. And then we have 2, 4, minus 5, 0, 0, and minus 0. Okay. So let's see what this will. This part is uncontrollable, which is going to be of dimension 3 minus 2, which is 1. And this is the controllability matrix, which is also is 2 by 2. This is just zeros. And we have some A1, 2. Similarly, there is this B vector. So this is BC, the controllable part. And now you can just check that we have the similarity transformation, which transforms the system into the standard form for uncontrollable systems. And you can also see that the pair AC is controllable. Sorry, AC and BC is controllable. So we can now simply check this. This is just a second order system. So BC and AC hence BC. This is 2024 and BC is 0. So we have 2 and 2. Matrix is 1, 0 and 2. You can just notice that this is non-zero, which implies that the pair AC-DC is controllable. Alright, so you have found out the transformation matrix. The controllable subspaces, so keyboard space of the transformed system. So the transformed system has these matrices in general: AC, A12, 0, AU. So this system is, so we have C bar, discrete C, image of I n bar by n bar times 0. Or so where n bar for our case is 2, because we had only 2 linearly independent vectors. Matrix controllability. Alright, so I hope that this question was clear to you. Yes. Next question then. So if you have any questions regarding the assignment or what we're discussing right now, you can just ask me here. Meanwhile, let's move on to the next question. And stabilizability of the entire system, the following matrices. See, so we have a 3 by 3 matrix, minus 1, 0, 0, minus 1, minus 4, 0, 0, minus 3, plus 1. Just check. And the B is the vector 1, 0, minus 1. To determine stabilizability using the PBH test, what we need are the eigenvalues of the system. So let's first compute the eigenvalues. So we have determinant of A minus lambda I. So minus lambda, minus for minus lambda, and then the rest of the entries of it, remember zero. This should be 0. So this is simply minus 1 minus lambda, minus 4 minus lambda, 1 minus lambda equals 0. And this is lambda plus 1. And this is lambda plus 4, and this is n minus lambda. So the eigenvalues are lambda equals minus 1, minus 4, and plus 1. Alright. So let's recall the previous test for stabilizability. So again, we have the matrix. It's the same matrix in both the previous tests for controllability and stabilizability. The rank should be n, the order of the system, but we have to check in this case for lambdas which have real part greater than 0 or equal to 0. So this is what's different as compared to the previous test for controllability. Right. So we just have one eigenvalue, which is lambda equals 1, for which this condition holds. Real part of lambda is greater than 0. So you have to get magnitude of the, just like in Germans. For our lambdas, this is just real part of lambda is greater than 0. Alright. So we just have to check for lambda equals 1. So then we have what's the rank for? A minus I, which is going to be minus 2, minus 5 and 0. Then we have the rest of the matrix. And then we have B. So B is 1, 0, minus 1. Check whether the rank is 0 or not. So for our case, the rank is 3. So we have to check if 3 rows are linear independent or not, or 3 columns. So this is anyway a 0 vector. Let's see. Alpha 1 minus 2 minus 1 0. 3 times the last column is 0. So we have to check whether this implies that all these 3 coefficients are 0. Alright, so let's check. The first equation is minus 2 alpha 1 plus alpha 3 equals 0, which implies that alpha 3 is 2 alpha 1. Then we have minus alpha 1 minus 5 alpha 2 equals 0, which implies that uh, alpha 1 equals 5 alpha 2, or minus 5 alpha 2. And then we have minus 3 alpha 2 minus alpha 3 equals 0. So we can just substitute this. So we have alpha 2 is minus 1 by 5 alpha 1, and alpha 3 is minus 2 alpha. So this just implies that alpha 1 is 0, which again implies that alpha 2 is 0 and alpha 3 is 0. Okay. Okay. Therefore, the rank of the matrix V minus lambda IV is 3 for lambda equals 1, which implies that the system is stabilisable. Right. So from the PBH test, you just have to remember this important difference, and this matrix for both the PBH test is anyways the same. Alright. So now let's move on to the next question. So consider the system. X dot equals AX plus BU, where you should make a system with matrix A as minus 2, 2, 1, and minus 1. B as the column vector 1, 1. And we have to determine which of the following statements is definitely true for this system. So you may have a similar question in the assignment. So the first statement is that the system is controllable. The second is the rank of the matrix. A minus lambda and B, the one which we use for the PBS test. It is 2 for all eigenvalues of lambda. Sorry, for all eigenvalues of A. Then we have the third statement. The system is not controllable. But stabilizable. Then we have part B, the null space of the controllability matrix. Is trivial. So a trivial subspace is the one which just contains a zero vector. Alright, so you can see if we calculate the controllability matrix, then we can figure out part statement A, statement D, and let's see maybe B also, right? Because it's the PBS test. So let's see. Controllability matrix for n equals 2 is BAB. And AB is simply minus 2, 2, 1 minus 1 times 1, 1. This is going to be 0, so 0 and 0. Therefore, C is simply 1, 1, 0, 0. You can see that there is only one linearly independent row or column, and also this is 0. Therefore, the pair AB is not controlled. So, we can eliminate this statement, and since the pair AB is not controllable, therefore the rank of the matrix is not going to be 2, right, for all eigenvalues of A. So we don't have to actually find out the eigenvalues not yet, but maybe we may have to calculate those for stabilizability. Before we do that, let's figure out the null space of the controllability matrix. So the null space is, let's denote the null space by n of A, which is also sometimes written as kernel of A. These are all vectors in Rn, for our case R2, such that Ax is 0. Alright. So let's write down what A is. Minus 2, 2, 1 minus 1. And let's say that the elements of the vector x is x1 and x2. 0. Okay. So we have to figure out what kind of vectors can be, what kind of elements x1 and x2 can be. So let's just solve this equation. This implies that x1 equals x2. Let me check. Sorry, we have to find out the null space of the controllability matrix. So this is not A, this is C. So C applied to X. Alright. So the controllability matrix is simply 1, 0, 1, 0. and we apply x1, x2 equals 0. So what do we have? We have x1 equals 0 from both the equations, and x2 can be any vector. So the null space looks like uh, the vector, let's say 0, x2, where x2 can be any real number. That the null space the controllability matrix is not trivial because it contains more vectors than the zero vector. So this statement is correct. And now we have to figure out whether the system is stabilizable or not. Okay, so now we'll have to find out the eigenvalues, okay? Determinant A minus lambda I is minus 2 minus lambda minus 1 minus lambda. This is A minus I, and the off-diagonal elements remain the same. So let's figure out this. Minus 2 minus lambda, minus 1 minus lambda, minus 2 equals 0. Since we have lambda plus 2, lambda plus 1, minus 2 equals 0, which is lambda square plus 3 lambda plus 2 lambdas, sorry, minus 2 equals 0, which implies that lambda square plus 3 lambda. So the eigenvalues are 0 and minus 3. So for stabilizability, remember that we have to check the rank of that matrix for uh, lambdas such that the real part of lambda is greater than equal to 0. For our case, we just have to check for this one. So this is nothing but rank of AB because lambda is 0. Alright, so let's write this down. The matrix A is 2, 2, 1 minus 1, and B is 1, 1. Alright. So you can see that these two columns are linearly dependent because minus 2, 1 times minus 1 is 2 times minus 1. So this is column 1, column 2, column 3. So you have some scalar multiply. Column 1 is column 2, therefore C1 and C2 are independent. So now you just have to check whether C1 and C3 are linearly independent or C2 and C3 are linearly independent. Let's check this quickly. Thank you. So we will have 2 alpha 1 plus alpha 2 equals 0 and minus alpha 1 plus alpha 2 is 0. This simply implies that alpha 2 is alpha 1. Substituting that here, we have So the rank of this matrix is 2 since we have only two linearly independent columns. You can also check for linear independence of the two rows by taking the linear combination and we get the same answer. Alright, so this is n. Therefore, the system is stabilizable. The system is not controllable but stabilizable. Alright, this question is clear to you. Now let's move on to the next part. So consider the discrete LTI system. System is given by x at k plus 1 equals 0, 1, 1, 1 times xk plus the b vector, that's 0, 1, b. So now we have to comment controllability and stabilizability of the system. Let's see. So this is for n equals to, we can quickly find out what the controllability matrix would look like. This is P and AB. So AB is 0, 1, 1, 1, 0, 1. This is 1, 1. Alright. So C looks like 0, 1, 1, 1. The determinant is clearly non-zero, which implies that the pair AB is controllable. Let's comment on the stabilizability of the system. So recall the previous test for stabilizability for discrete system. That's a little bit different. The discrete time LTI system is stabilizable. So we have an if and only if condition. We have rank of A minus lambda I B should be n for eigenvalues such that their magnitude is greater than 1. Alright, so for this we need to first find out what the eigenvalues of A are. And determinant of A minus lambda I, that's minus lambda, 1 minus lambda, 1, 1, is equal. Okay. So this implies that Yeah, minus lambda 1 minus lambda minus 1 equals 0. This becomes, so let's see what are the roots of this equation. We have minus b plus minus b squared. So a squared minus 4ac is minus 1 upon 2. 1 plus root 5 by 2, 1 minus root 5 by 2. So this is a multiplication 1 plus 618 and minus 0.6183. So we just have to check for this eigenvalue because the magnitude of this one is less than 1. Okay. So a minus lambda I for this lambda. I'm just going to write this down directly. So we have minus 1.61811 and here 0.618. Neutral and negative sign. Alright. So the rank of the matrix A minus lambda I, and then B, we have B is 0, 1. I have to check whether this is 2 or not. Okay. So let's see if we have two linearly independent rows. So yeah, there's alpha 2 times 1 and 0.618 1 equals 0, 0, 0. Alright, so let's see the third equation. So this is going to be 0 times alpha 1 plus alpha 2 equals 0. And then you can just substitute, right? So minus 1.618 alpha 1 plus alpha 2 equals 0. And substitute alpha equals 2 equals 0, which implies that alpha 1 is also 0. So we have rank equals 2. Therefore, the system is stabilizable. Alright. So if you have any questions regarding the assignment or the questions that you have to leave out, you can ask me right now, I guess. Before we move on to the next question. Alright, if not, let's move on to the next question. This is question 6. So Now consider the LTI system. X dot equals -1 to -2 minus 1 times x plus 1 0 times 0. Right. So the system is discretized for implementing a computer control algorithm. And the sampling time is equals pi. So we have to comment on whether the resulting system, with the resulting discrete time system, is first controllable, then we have only stabilizable, have C uncontrollable, and then D. So the first thing that we should check in a system which has been discretized is to find out if the original continuous time system is controllable or not. So if it's not controllable, then the discretized system would also be not controllable. So let's see, we have C equals BAB. AB is -1, 2, and -2 and -1, 1, 0. So we have -1, -2. So this is clearly controllable because the determinant is non-zero. So the pair AB is controllable. And now we can check whether the discrete pair is controllable or not. So to find that out, we don't have to again compare AD and BD. We can first find out the eigenvalues of the matrix A. Alright. So let's figure that out. Eigenvalues of A. This is determinant of -1 minus lambda 2 minus 2 equals 0. So this becomes plus 4 equals 0. Right, so this is lambda square plus 2 lambda plus 5 equals 0. We have lambda equals minus b plus minus b square minus 4ac upon 2. This is 4i by 2. This becomes -1 plus -2y. Okay, so we have complex eigenvalues of A. Now let's recall. So this is the remark on slide 77. Suppose A has complex conjugate eigenvalues. Alpha plus minus. We have two conditions. The first one is if the sampling period T does not equal to any integer multiple. Beta. The discretized state equation is controllable. And similarly, we have the next statement that if T is equal to m times pi by beta for some integer m, a discretized system to control it. So we have, according to the question, equals pi, alpha equals -1, and beta equals 2. So is pi equal to, so we have T equals pi, which is m times pi by 2, measured by 5. M is an integer. Alright, so the system may not be controllable, so we have to find out what the discrete matrices are. Alright, so AD is to the power 80 and BD is 0 to T times B. So e to the power 80 for LTI system is simply Laplace inverse of Si minus A inverse. So A is, okay, write this down. Si minus A is S plus 1, S plus 1 minus 2, 1. So now the inverse is simple since it's a 2 by 2 matrix. 1 upon determinant of the matrix. Then we swap these two and we have 2 1 minus 2. Okay. So we have the characteristic equation below, which you already know. That is s square plus s plus 5 s plus 1 2 minus s plus 1. Yeah. Alright, let's see. So we have the roots alpha plus minus beta I. We have, so we have actually uh, S alpha is minus I. So we have plus 1 minus 2I. Then S plus 1 plus 2I. Or J if you want it to be. S plus 1, S plus 1, 2N minus 2. Alright. So now we can figure out the Laplace inverse of this whole quantity, the partial fraction expansion of each of the elements of the matrix, and then find out e to the power 80 and substitute here and here. And then you can just form the controllability matrix VD and AD times D. So we verify whether the discrete system or the discretized system is controllable or not. And then similarly to figure out stabilisability, first find out the eigenvalues of lambda d, ed, computation of ed minus lambda I dd. And since this is a discrete system, for all lambda complex such that real part of not real part magnitude of lambda is greater than equal to 1. Alright, so I'm going to pause for a few minutes and you can ask any questions if you have any. Alright, so if there are no questions, we'll move on to the next one. We again have a question based on discrete systems. Question 7. So we have just seen how to comment on stabilizability and controllability of a discretized system. So consider the LTI system. A equals 0, 1, 0, 0. B equals 0, 1, 0. 1 and C equals 0. So we have to determine the values of T, which is the sampling time, that preserve controllability. Or let's see whether the system itself is controllable or not. So we have C as B and AB. 0. We have 1, 0. So this is 0, 1, and 0. And this implies determinant of C is non-zero, which implies that the pair AB is controllable. Now we have to find out AD and BD. So AD again is e to the power A, sampling time T. BD is 0 to T, e to the power AT BD. At any time T is Laplace inverse of SI minus B inverse. Now we also have extra equals say zero state response, which is let's say we have 0.00 and this x1 dot x2 dot. This implies that x2 dot is 0. X1 dot is simply x2, which implies that x1 at time t is let's just see which is fine. Mhm. Yeah, this I can just check once. Just a second. So we have to figure out what the state transition matrix is. So let's see. Si minus A is S minus 0, S minus 0, minus 1, and 0. So we have S minus A inverse as 1 upon determinant of A. And we have this 1 and 0, which is simply 1 over S, 1 over L. It's inverse of 1 over S. So this is simply step input, and then we have T. Let's see. Alright. So at some sampling time, let's assume that it's capital T. We have 1, T, 0, and 1. Now we need to, this is the discretized A matrix. Now we have to figure out what BD is. This is simply 0 to T e to the power 18 dt times B. Alright. So let's see. Then we have 0 here and 0 to T. This should be multiplied by B. So we have 0, 1. So this is 0 to T to T, and then 1 T. We have T square and T. Alright. So the system is BD is 1 T 0 1. BD is T square T. This is okay, sorry, this is small t, and when we integrate it, this becomes T square by 2. So we write this down here. Alright, now let's form the controllability matrix. I'm going to denote this by, let's see, CD equals BD, AB, and B. So we have this matrix, which is 1, P 0 1, T square by 2, and T. This is t square by 2 plus t square, and this is t, which is 3t square by 2 and t. Alright, so the controllability matrix is t square by 2 t, 3t square by 2 and t. So this is good in the square matrix. Determinant of this is t cubed by 2 minus 3 t to the power 4 by 2 equals 0. Sorry. So we have this. And if we want it to be controllable, this should not be equal to 0 for the pair medium BD to be controllable. You have to figure out, you have to determine the values of the sampling time t, which preserves controllability. Alright, so let's see for which values we have 0. This is P2 minus 3P4 equals 0. 0, and for sampling time, so the pair ADBD is controllable for all sampling times. So for all t in R, which is around 0 and 1 by 3, and positive real numbers, so R plus. So I hope this question was clear to you. There's a similar question in this week's assignment as well. So next question number 8. You just have to figure out the discretized matrices. It's question 50. Sorry. I guess it's 8 now. Alright. So I hope this question is clear to you. Now let's just see. One more question before we end for today. We have already seen a part of this question in the previous session. So I'm just going to revise that a little bit. This is the last question. This is for LTI systems. So consider the following system. X equals 1 0 0 1 0 0 minus 1 x plus b1, b2, b3 times c. So we have already solved the first two parts of this question. So b1, b2, b3 are unknown scalars. The first part of this question is provide an example of the values of b1, b2, b3 for which the system is not controllable. Then we have the values of b1, b2, b3 for which the system is controllable. Then we look at the C part today. Provide necessary and sufficient condition. On the scalars b1, b2, and b3 so that the system is controllable. In the first two parts, we just have to form the controllability matrix. C is, and then find out or just give an example for which this is full rank or this is not full rank. So this is not equal to 3 or equal to 3. Now let's come down to the last part of this, which is C. So recall that for the system to be controllable, the necessary and sufficient conditions are that the eigenvectors of A transpose cannot lie kernel of B. B transpose for the pair AB to be controllable. So for this, you first have to find out what are the eigenvectors of A transpose and then figure out if they lie in the kernel of B transpose or not. Okay. So A transpose is 0, 0, 0, 0, 0, 0, minus 1. Okay. Then the eigenvalues can be determined by determinant of A transpose minus lambda are equal to 0. I'm going to write this down directly. Lambdas are 0, 1, minus 1. Now we know how to calculate the eigenvectors. For example, for lambda equals 1, we have A transpose acting on an eigenvector V equals lambda times V. So this means we have 1, 0, 0, 0, 0, minus 1 acting on V1, V2, V3 is 1 times V1, V2, V3. Now you can calculate what this should be. So for example, one of the values which V1, V2, V3 can take is 0, 1, 0. Linear dynamical system, I think the professor has given some references. Let me check. Just a second. Yes. So I think he has given some references. Those are the ones which I refer to as well. So you can check out the, I think, the announcements or the about the course tab. And I guess some of the references are, I think it's CT Chen, Linear System Theory and Design. What your book is J.P. Spanner. You can refer to this book, A Linear Systems Theory, which I would say is it's PJ. You can just write this down. And Ian Micro. It's, the name is Linear Systems. So you can refer to anyone else. All right, so getting back to the question, the yeah, the three eigenvectors are, so we have 1, 0, 0. You can try calculating these. 0, 1, 0, and then 0, 0, 1. All right, now you have to check whether these eigenvalues are in the kernel of B transpose or not. So B transposes B1, B2, B3 of B transposes all those vectors x which have, let's say, component x1, x2, x3, which can map to 0. So we have to check whether the eigenvectors, let's say, v1, v2, and v3 lie in the kernel or not. So let's say if this applied to 1, 0, 0 is, so this would imply that b1 is 0. So b1 is. So I guess the necessary and sufficient condition is they cannot lie in the kernel of B transpose. So B1, B2, B3, this B transpose acting on any eigenvector B1 should not be 0. This implies that B1 can never be 0. Then similarly, we can figure out that B2 and B3 can also never be 0 for the system to be controlled. Alright, so these are the necessary and sufficient condition for the pair A B to be controlled. Alright, so I hope that the questions that we discussed today were clear to you. Um, Alright, so let's end for today if there are no more questions. Yes, alright, thank you. Let me just check. Okay, so I cannot unmute you just one second. I think there is something in the settings. Did you try unmuting yourself? Because I don't have that option now. Or maybe you can just type your question. I'm not sure what was this covered in this week's tutorial or you just asking generally? Oh, sorry, this week's lecture was just about controllability, I guess. I don't think we covered those in this course. We talk about stabilisability and controllability of LTI systems and a few the linear LTV systems. Yeah. All right. Okay. Thank you. Let's end for today.